Hello friends, welcome to new edition of Solar Feasibility Spreadsheet, and in this edition I will tell you improvements and developments in this spreadsheet over a period of time. Now as we all know that this spreadsheet, it helps you in designing the complete solar power system, and finally it will let you know the complete profitability of that solar power system. So in short, it tells you whether the system is profitable or not, whether the system is going to provide you the return that you have expected or not. Initially, I started with only two countries when I launched this solar feasibility spreadsheet, and that were India and United States of America. But over a period of time, this solar feasibility spreadsheet has become more versatile, and a total of 11 countries are now added in this spreadsheet. These are, in addition to India and United States of America, these are Australia, South Africa, Jordan, UAE, Brazil, Argentina, Mauritius, Kazakhstan, Dominican Republic, and Panama. So people living in these countries can avail the benefit of this feasibility spreadsheet and can design the system and can know the overall profitability of the solar power system beforehand. Okay, let us proceed. Now let us select country United States of America. And under select state column, I'm selecting California. Now we can check out the graph in front of you. This graph tells you the average peak sun hours in that particular location in California. And anything above 4 is considered very good. So California receives 5.73 peak sun hours, and it is considered very good for solar power installation. So people living in California are in benefit of good amount of sunlight. So let us proceed further under calculate load tab. So in this tab, you will select the electrical appliances that you want to run on solar power. Say for example, I select ceiling fan, and under column C, you will find the watt range of that particular electrical appliance. Ceiling fans are generally under 20 to 80 watts. My ceiling fan is 60 watts, so I have written 60 watts, and I want to run say 6 ceiling fans on solar power. You can check out that total loads of 6 ceiling fans of 60 watt each comes out to be 360. And similarly, you can select other electrical appliances that you want to run on solar power, and you will get the total load of all the electrical appliances under column G. So these are the electrical appliances that I want to run on solar power. Total watt of all these electrical appliances comes out to be 2760 watts. So in this way, you can calculate the total load of all the appliances that you want to run on solar power. Now coming to energy consumption tab. In this tab, you will find the average use of each electrical appliance in a day. So for example, my ceiling fan runs on an average of 6 hours per day. Similarly, CFL for 4 hours, desert cooler 2 hours, television for 4 hours, washing machine 2 hours, booster pump. So energy consumption of ceiling fans comes out to be 2160. When I multiply 360 watts by 6 hours, it comes out to be 2160. So under column C, you will find the energy consumption of each electrical appliances, and total energy consumption comes out to be 6160 watt hour. So this is the amount of energy that my solar panels should produce to run my electrical appliances. Energy consumption chart is the pictorial description of the amount of energy consumed by each category of electrical appliance. Now coming to the sizing tab, this section will tell you the overall technical design of the solar power system. Country is United States of America, city is California, state or city, average peak sun hours 5.73. So you will find all the details that we already have filled in the previous section. So size of the solar panels in this case 1604 watts. So 1604 watts of solar panels are required to meet my energy needs. Inverter rating would be 1925. Now you can see that we have considered number of losses while designing the overall solar power system. Temperature loss 10%, dirt loss, transmission inefficiency loss, shading loss, manufacturer tolerance loss, inverter inefficiency loss. All these losses are considered, and the total loss in the system comes out to be 33%, and this is a good amount of loss. So I have considered all the relevant losses that a solar power system can undergo. On this basis, we have calculated the profitability of the solar power system. So in case you want a battery backup, you can give your inputs here, enter the number of days of battery backup. Say for 1 day, you can write 1. Efficiency of battery 90%, enter the depth of discharge 80%, and accordingly the sizing of the battery will come out. Now you can see that maximum capacity of the battery required to provide you 1 day of battery backup comes out to be 360 ampere hour, and the charge controller rating comes out to be 80.2 ampere. Now you can see that your solar panel angle with respect to horizontal comes out to be 31.45 degree. It means that you should give a tilt of 31.45 degree with respect to horizontal to get the maximum amount of sunlight falling on the solar panels. And the facing of solar panel should be in the direction of south. So in that way, you can design the overall solar power system. My system, in my case, the system is without battery backup. So I am writing 0 here, 0 here, and 0 here. This is my solar power system without battery backup. Now coming to the costing section. So under costing section, you will be writing the cost that you have incurred while purchasing the overall solar power system and installing on the rooftop. Enter the cost of the panels. Say cost of the panels are $2,000. Cost of batteries are not required. I do not need a battery backup, so I will not write any value here. That is 0. Cost of inverter, say $800. Cost of charge controller is not required. Charge controller is required when there is a battery backup. Enter the cost of racking or mounting structure, let's say $1,000. Enter the cost of installation, labor, another $1,000. Miscellaneous cost, say $200. So overall cost of the system comes out to be $5,000, and the average per unit cost comes out to be 3.12. Now let's say your government is offering you 20% tax credit for purchase of solar power system. So you can write 20% or 25%, whatever is the case. Let us write 20%. So total rebate and tax credit comes out to be $1,000 of, that is 20% of 5,000. So in that case, average cost of the system after incentive comes out to be 4,000 USD. And average per unit cost per watt after incentive comes out to be 2. I think it is clear now. Coming to energy chart section. This section will tell you how much units or how much energy your solar power system is going to produce under different months of the year. You can see that your average energy need is 6160 watt hour, while your solar power system is producing different values in different months of the year. In the months of January, February, March, October, November, and December, your solar power system is producing less energy than what you are expecting. While in the case of April, May, June, July, August, and September, your system is producing excess of energy than what is required by you. So in the months when your system is producing surplus energy, you can feed to the grid through net metering system, and the grid will compensate you for those extra units. So this energy chart shows you where your system is energy deficient and where it is providing more than what you are expecting. Now coming to another section, that is assumption. From here we start the financial profitability of the solar power system. The first input is please enter the per unit rate of grid electricity. Say for example, the grid rate in California is say 18 cents. You should write 18 cents. Now enter the escalation rate in grid. Escalation rate is 4% per year. This rate is generally taken as the average of last 5 to 10 years. Now we can check out that in year 1, you would be paying 18 cents per unit to your grid, while in the year 25th, while in 25th year, you will be paying 46 cents for the same unit you are consuming right now. This shows that how grid electricity rate are going to increase over a period of time in future. And the maintenance cost of the system. As my system is grid tight system without battery backup, so my maintenance cost would be less because solar panels maintenance, they require little maintenance like cleaning, checking of connections, etc. So in that case, my maintenance cost would be say 1% of the total cost of the system. So I will write 1%. And I have taken increase in maintenance cost by 5% every year because my system is going old day by day. And with every passing year, my system would be needing more care, and I need to shell out more money to take care of my system. Now coming to debt equity structure. The debt equity structure helps you in deciding the cost of capital. So for example, if you have invested your own money, in that case, the cost of capital would be 10 or 20-year government bond yield. But if in case you have taken certain amount of loan from lender, then in that case, the overall cost of capital would be weighted average, your risk-free return from government bond, and interest rate that is charged by your lender. For example, I'm writing my risk-free return as 3%. That is the 10-year or 20-year government bond yield in my country, 3%. Now my weighted average cost of capital comes out to be 3%. It means that my solar power system should produce at least 3% so that it becomes profitable. Okay, now let us understand from another point of view. For example, I have borrowed $2,000 from a lender. In that case, my own investment would be $2,000 and borrowed amount would be $2,000. Total cost of system would be $4,000. Now this borrowed amount $2,000 I have taken as 5% per annum rate of interest, and duration of the loan is 5 years. Now you can check out my weighted average cost of capital now becomes 3.2%, and earlier it was 3%. So my weighted average cost of capital has increased because I have borrowed certain amount at higher rate of interest. So if my solar power system now my solar power system need to produce at least 3.2% to make it a profitable project. Now coming to overall financial profitability of the solar power system. Here we come. Now the actual cost of the system comes out to be $4,273. It has taken into consideration the interest rate also. So instead of 4,000, my actual cost of the system has increased to 4,273. Internal rate of the system. My solar power system is going to produce 9.2% per year. So it is a profitable project. While my cost of capital is 3.2. So 9.27 is very much above 3.2%. The net present value of the system is $3,917. Net savings in 25 years, $8,320. And the payback period would be 11.6 years. Yes, it is a feasible project. Solar electricity cost per unit would be 6 cents, while the grid rate is 18 cents. And the average unit generated per month comes out to be 165 units. Yes, your solar power system is 190% more profitable and efficient than the grid electricity. So this is the payback period chart. You can check out. This is the overall financial feasibility of the system that shows that your system is very much profitable under the condition that we already have entered. Okay, now let us understand the break-even cost also. Break-even cost is $7,286. It means that below this cost, your system is profitable, and beyond this cost, your system would not be profitable. That means that your system would be producing less than 3.2% beyond $7,286. So in this way, you can find the overall financial profitability of the solar power system and can also design it technically. And if any one of you want to avail the benefit of this solar feasibility spreadsheet, you can check out the link given in the description box. So that is all from now. We will be discussing some more improvements and some more developments in solar feasibility spreadsheet from time to time. Till then, goodbye. Have a nice day.